So for this lecture, we're just going to do some torque examples and we're just hopping right into it. So I'll read you the problem. A vendor hangs an 8 kilogram sign in front of his shop with a cable held away from the building by a lightweight pole. The pole is free to pivot about the end where it touches the wall. What is the tension in the cable? Um, oops. So something we haven't done yet because our torque problems have had, like the forces have already been drawn for us. So we haven't done what I call extended free body diagrams, which is just a free body diagram, but we draw out the object so that we can indicate where the forces act on it. Okay, so here is our lightweight pole. Just trying to look for what language they use. Lightweight pole, put the X where the pivot is, that's where it's attached to the wall. And then we just draw our forces. So the sign that is at the end, and we will just say that F sub S for sign. And then the cable is at an angle. Maybe that's too big of a force, probably. My scale is probably off here, but that's the tension in the cable. And then one more thing we can say, this is a 60-90, 30-60-90 triangle. So we can say this angle is also 30 degrees. And now, the question says this is a lightweight pole. That tells us we don't have to worry about the mass of the pole. That fact and also that they didn't give us the mass of the pole, both are why we can ignore that. But if we were given the mass of the pole, we would put if it says uniform pole of mass blah, we would put that force right here in the middle. So I think another example will show that, but just so you know, in this example, we don't have to do it because it doesn't give us a mass of a pole and it says it's lightweight, which is just like physics language for you can ignore its mass. And then the other thing with torque is the distance, and I don't think actually the prompt says, but this is a 1 meter long pole. So, and both of the forces are acting at that length. So that's nice. It simplifies things. Okay, now we do our torque table. Force, distance, angle, and instead of writing clockwise, counterclockwise, I'm just going to write plus or minus. So let's do the force from the sign, which is just going to be the weight of the sign, so the mass of the sign times the acceleration due to gravity. And the distance is 1 meter. That angle is 90 degrees. And let's see, that's going to cause clockwise rotation, so that's negative. And then our tension, just T, is at 1 meter also, and this one's at 30 degrees, and that's going to cause counterclockwise rotation, so that's positive. So now we're trying to find what the tension is, and we know that the net torque is 0. There's not rotation happening here. So we can use that to solve for the tension. So let's see, tension times 1 meter times sine of 30 degrees minus the mass of the sign times g times 1 meter sine of 90 degrees. Okay, and then we can add this term to both sides so that we have tension times 1 meter sine 30 equals mass of the sign times g times 1 meter times sine 90. And then I'm just gonna ignore the stuff that is all 1, because if you multiply by 1, you get the same thing you had before. And then I'm going to divide sine 30 on both sides. So that tension is by itself. And so we have the mass of the sign times g divided by sine of 30. And the sign is 8 kilograms, 9.8 meters per second squared. divided by sine of 30 degrees. And this gives us a tension of 156.8 newtons. And now you could round that to 157 or even 160. I'm not going to do that right now because I want us to do another part of the problem. And so it's better not to round too soon. So for the next part, which isn't in the problem statement, but we want to know what are the X and Y components of the force on the pole from the wall. So the W here is the wall, so that the net force is 0. So we have forces acting here on the post, but that didn't matter to us when we solved initially because that is the pivot point. So it doesn't matter what forces act on the pivot point, it doesn't cause torque. So now we can think about this instead of as a torque problem, we can think about it as just a force problem, and we can just do a regular free body diagram. And we have, let's see, we have our tension force, and then the force from the sine. And then I'm just gonna well, if in order for our net force to be 0, we're gonna need to cancel out that X component of the tension. So there's definitely gonna be a positive X component of this wall force. And then I'm just gonna guess for the Y component, I'm gonna say maybe it's down. And if you guess wrong, it'll just come out with a negative sign and you'll be like, oh, my bad, it's supposed to be up instead. And then a different color. Let's make sure we do our X and Y components. X, and this is that angle theta, or 30 degrees, not 50. So let's get those X and Y components. The Y component, that's going to be sine, because it's opposite the angle, sine theta. So this gives us 78.4 newtons. And then the X component is cosine, and that gives us 135.8 newtons. So let's do our force equations. F net X equals 0, and that equals the X component, or yeah, the X component of the wall force minus the X component of the tension, and those are the only forces in X. So we see that the force in the X direction on the pole from the wall is just equal to the X component of the tension force, which we just calculated is 135.8 newtons. So that's the X component. Let's see about the Y component. F net Y equals 0, and that equals the tension in Y minus the sine force from the sine and the Y component of the wall force. Yeah, so let's just see what we end up with. Yeah, no, sorry, I'm mixing myself around. We will put the wall force, we'll add it to both sides so that we get the tension in Y minus the force of the sine, and that will tell us what our Y component of the wall force, or the force from the wall, is. So tension in Y we found is 78.4 newtons, and then the sine weighs 8 kilograms times 9.8 meters per second squared. And oh, this is subtracted. And we get that this is 0. So there is no Y component of the force on the wall, or from the wall. There's only the X component. So good to know. Okay, so that's that first example. And again, we did a new thing, which was draw an extended free body diagram. And we're going to practice that more. And then we did our torque table, which we've been doing, and then we solved torque to get the tension. And then we thought back to forces so that we could also find any forces that the wall applies to our system. Because it doesn't cause any torque, but it is a force. So it does contribute to our net force. Okay, let's do another example. And this time I'm not going, in my extended free body diagram, I'm not going to ignore the forces acting on the pivot. I'm going to draw it in my extended free body diagram. Let's pause and read the problem. A participant in a strongman competition uses an old-fashioned device to move a large load with only muscle power. A 1 ton or 910 kilogram bucket of rocks is suspended from a sturdy, lightweight beam 0.85 meters from a pivot. The man lifts the beam at its end 3.6 meters from the pivot and holds it steady. How much force must the man apply, and what is the force on the beam from the pivot? So to start our extended free body diagram. Okay, so let's see. The man is holding it up, so his force is going to be pointing up, force from the man. And then the rocks, those are hanging down, so we're going to have, we'll just call this force from the rocks. And then the pivot, it's definitely, there's definitely a force, and it's not going to affect our torque, because it's at the pivot point, but we'll just guess. We'll guess that it's up, force from the pivot. And then let's draw out what our distances are. So for the force from the pivot point, it is at the pivot point, so that's 0. This one, what did they say? 0.85 meters. And then the man is holding it all the way at 3.6 meters. Okay, torque table, force, distance, angle, plus or minus. And the angles for all of these are 90, so already did that part, done. Okay, so we have the forces from the man, and we're trying to figure out what that is. We don't know what it is. So when that he acts at 3.6 meters, 90 degrees. And let's see, that's going to be clockwise rotation, so it's negative. And then the force of the rocks, that's just going to be the weight of the rocks, so their mass times G. That's 0.85 meters from the pivot, also 90 degrees. And that would cause counterclockwise rotation, so that's positive. And then we can write the pivot force in our table, but the distance is 0, so we kind of just stop there. Okay. So we have the net torque equals 0, and it is these two torques combined. So let's see. I'll write the positive one first. So mass of the rock times G times 0.85 meters times sine of 90 minus the force that the man applies times 3.6 meters sine 90. So both of these sine 90s are just 1, so we're gonna just ignore them. And then we're solving for the force of the man, so let's add that that times 3.6 to both sides. So we have mass of the rocks times G times 0.85 meters equals the force the man applies at his distance of 3.6 meters. Okay, and then we divide that 3.6 on both sides. So we end up with the mass of the rock times G times 0.85 meters divided by 3.6 meters equals the force the man applies. Okay, now let's just plug it in. So the rocks are 910 kilograms times 9.8 meters per second squared. 0.85 meters divided by 3.6 meters. So the force the man applies is about 2,100 newtons, but I'm gonna write the whole thing, 2,106. But again, you can round a little bit. Cool. So that's the force the man applies, but then we also want to know what force the pivot applies to. So, and this is where we can just do regular force. So we'll just draw our free body diagram. And let's see, we had the force of the rocks going down. We have the force by the man, and then the force by the pivot. Also, I'll just put that going up because that's what we drew on our set of free body diagram. So the net force in Y is 0, and that is the force of the man plus the force the pivot minus the force of the rock. And so we're trying to solve for the force of the pivot. So we will separate these. So we have the force of the pivot on one side, and then we have the force of the rock minus the force of the man on the other side. And again, if this came out negative, we would know that, oh, actually the pivot force is down instead of up. So let's see, 310 kilograms times 9.8 meters per second squared minus 2,106 newtons. And we get 6,812 newtons for the force of the pivot. So this is a strong man competition. I would say it's a strong pivot competition because the pivot is doing way more of the work. But yeah, again, so we drew our extended free body diagram, did our torque table, solved for whatever force was missing, and then we knew that the net, not only was the net torque 0, but the net force is also 0. And so we could find the force that the pivot point applied. And we found that it's much bigger than the strong man's. Okay, last example. This one's kind of weird. So what this is a sort of crane system, where there's like these two, what do they call them? Plate, like top and bottom plates, and then there's strings attached to a beam, and then you can hold a heavy object. So it's a crane, but you don't have to properly visualize the situation, like what that would be in life. We can just look at our diagram and work from there. But let's read the problem. A rigid uniform horizontal bar of mass 1 equals 90 kilograms and length equals 5.6 meters. It's supported by 2 vertical massless strings. String A is attached at a distance D equals 1.6 meters from the left end of the bar and is connected to the top plate. String B is attached to the left end of the bar and is connected to the floor. An object of mass M2 equals 300 kilograms is supported by the crane at a distance of 5.4 meters from the left end of the bar. Okay, so this is more complicated problem than the other ones. There's just more forces. Sorry, one. Sorry about that. I was just checking to make sure we didn't skip over the mass of the rod in the previous problem, but it says a lightweight rod. But this time we have to pay attention to the mass. So let's see. We have tension B at like the left end, and then tension A. We'll add the distances in a minute. And then the beam itself, its mass matters. And when it says uniform bar, I guess is what it says instead of beam, it's telling us that you can assume that, like, you can imagine that all the mass is at the center. We didn't really talk about center of mass that much, or really at all, I don't think. But that's what that is telling us, is that, okay, you do have to care about how much the bar weighs, but we can just, because it's uniform, we can assume that the center of mass is where it's all Oops, that's the eraser. There we go. So here is the weight of the bar. And then we have this other mass. And so we have the force from the force of mass 2. Okay, so those are our forces, but then let's do our distances. So initially for our, sorry, I'm getting ahead of myself. Really quickly, first, in a situation like this one, where there isn't necessarily a distinguished pivot point, we can decide where the pivot point is. And since we're looking for the tensions, which, sorry, I didn't say that, we're looking for the tensions, it makes sense to choose the location of one of the tensions to be the pivot point, because then we can solve for the other one with torque, and then the one we're using at the pivot point with force. So we are going to take our pivot point to be where, like at where string B is attached. And we'll solve for string B with force, or tension B with force. Okay, so its distance is 0. Plus also all of the distance are given to us from that end. So it makes sense to use it. I think that's kind of the intention. Okay, so this one, the distance is 1.6 meters. And then for the beam itself, or the bar, I guess, this distance is going to be the length of it divided by 2 halfway down. So 5.6 meters divided by 2. And then finally, mass 2 is located 5.4 meters. So they give us a distance x of 5.4 meters. Okay, so standard free body diagram, we figured out our distances. Yeah, this is a weird looking problem, but it's got the pieces we're used to. Okay, let's do the torque table. Force, distance, angle, positive or minus. And all of our angles are 90, so that's helpful. It makes it a little bit easier. And we'll go from left to right. So tension B is that first force, but it's at a distance 0, so no torque. And then we have tension A, which is at distance B, which is 1.6 meters. Angle is 90. And let's see, that would cause counterclockwise rotations. That's positive. Then we have the weight of the bar, which is at a distance L over 2, which is 5.6 divided by 2. And also 90. This one would cause clockwise rotations, so that's negative. And then we have the force of mass 2. And that is a x away, so 5.4 meters. 90 degrees still, and that one is also going to be negative. Okay, cool. So, net torque. And this time I'm not gonna put, like, I'm gonna wait to add numbers. So just heads up, that's like a little bit different than what I've been doing. So net torque is 0. We have TA times the distance sine 90. That one's positive, minus the weight of B times L over 2 sine 90. Together, yeah. Minus the force from mass 2 times x sine 90. Okay, so all of those sine 90s are 1, so we can just ignore them. And we are solving for tension A, so let's add the other 2 terms to the other side. So we have tension in A times the distance for A is equal to the weight of B times the length divided by 2 plus, they're added to both the other side, force of mass 2 times x, its position. And then we just divide that distance on both sides. So we end up with tension in A is the weight B times L over 2 plus the force of mass 2 times X divided by D. Now we'll plug in our numbers. Okay, let's see. Maybe I'll actually take up a little more room. We'll move over here. So tension in A equals weight B. So our beam has a mass of 90 kilograms, or a bar, I guess is what they're calling it. 9.8 meters per second squared, and then 5.6 meters divided by 2 for the distance. And then we add, and let's see, the object has a mass of 300 kilograms and 9.8 meters per second squared, and then X is 5.4 meters. And finally, we divide by the 1.6 meters where the tension in A is located. Okay. And this gives us tension in A of 11,466 newtons. So it's pretty big because this is like a crane system. Okay, cool. So now I want you for your post-lecture assignment to find the tension in B. And remember, we are just doing, it's just what we've done is just the, do a regular net force situation. Draw your free body diagram, write your force equations, and solve for tension in B. Okay, cool. So those are your torque examples. Yeah, have a good day.